Assalamu alaikum viewers, and welcome back with one more example of your mathematical induction. And those people who have just viewed my previous two videos related to this topic wouldn't find much difficulty in understanding this example. And as I have explained that this mathematical induction comprises three steps. In the first step, we just try to prove that this series that we represent as P of n is true if we put n equals to 1, because you know that sequence is a function whose domain belongs to the set of natural numbers. So in the step 1, we just substitute n equals to 1 in the general formula of this series at the left hand side, and at the right hand side, this is the expression given to us, that the sum of all the natural numbers belonging to this series should give me an answer that should be equal to this format. Okay, so let us now, in step number 1, let us check that if we substitute n equals to 1 over here, then are the both sides satisfied or not. Okay, so let's have a look on this. So this is the general form of the series at the left hand side, and this is the expression present at the right hand side, that is the summation of this series should be equal to this form. So I just put n equals to 1 at both sides and I keep on solving. Okay, so I come to know that both sides are same, both sides are satisfied when your n is equals to your 1. So this thing enabled me to assert that P of n is true for n equals to 1. This is your step number 1. Okay, we have just taken the we have just broken the ice in that way, that for the first natural number, this series is satisfied. Okay, this series is equal to this. Now in the next step, we are just going to put down the hypothesis that suppose that your P of n is true for n equals to k. So wherever you're having your n over here in this question, you can see you just substitute n equals to k there, and it looks like this, and you just name it equation number 1. Now in the next step 3, you have to prove that if your P of n is true for n equals to k, then it should be true for n equals to k plus 1. Okay, for that purpose, what you have to add at both sides, I told you already in both of my previous videos, that what you have to add at both sides, that thing you just find by substituting n equals to k plus 1 at this general form of your series. Okay, so let's do some rough work in order to find what you have to add at both sides. So let us do a bit rough work here. Okay, so I'm going to put n equals to k plus 1 over here, so it looks like this. It is 2k plus 2 minus 1 give you 2k plus 1, and 2k plus 2 plus 1 give you 2k plus 3. Okay, so this is something that you are going to add at both sides of this equation number 1. Okay, so when you just add this term at both sides of this equation, and then you start solving this right hand side after summing up this term, then what you should get in order to put down the statement that P of n is true for n equals to k plus 1, you should get this answer on solving the right hand side. What you're going to get, let me do the rough work in this respect as well. If you substitute n equals to k plus 1 in this expression, that answer is something that you should get after solving the right hand side. So it should look like this. The substitute n equals to k plus 1 here, so it is your n, and this is your n plus 1 upon, and this is your 2 times 2n plus 1, so it is going to be 2 times 2 k plus 1 plus 1. Okay, so actually you are having so this is something that you should get after solving your right hand side once when you add this term at both sides. Okay, so let us add this term at both sides of your equation number 1 and move ahead to the step 3. Okay, so once when I add this term at both sides of equation number 1, I just start my step number 3 and I add this term at both sides of my equation number 1, and that's how the thing is going to be. Okay, now I have to solve this right hand side over here, and on solving I should get this form. Okay, in order to make it true, this p of n true for n equals to k plus 1. Okay, now let's start doing some basic preliminary algebra here. You can see that in these two terms I'm having k plus 1 common in the numerator and 2k plus 1 common in the denominator, so I'm going to take them out. Okay, and then the further solving work is going to continue. So I've just taken out k plus 1 common from both numerator and 2k plus 1 common from the denominators of both these terms, and the remaining terms so left inside looks like this. Now I have to take out the LCM of these two algebraic fractions. Okay, and after that how the term is going to look like, let's see. Okay, I've just taken out the LCM and that's what I'm getting here. Now what I have to do now, I'm going to multiply this k with both these terms and this 2 with both these terms. Then further I'm going to simplify the numerator. Okay, and definitely I'm going to get a quadratic equation here in the numerator. Okay, so once when I multiply this k with my 2k, it becomes 2k squared. Okay, and then plus 2 k into 3 give you 3k, and then 2 into k they give you 2k, and 2 into 1 give you 2. Okay, and you should keep in mind the signs because it really counts a lot in algebra, you know that. So that's how this thing is here, and you can see now you're having two terms involving k, so you just simplify them and it gives you 5k. So the quadratic equation now is going to be 2k squared plus 5k plus 2. Okay, so this is something that I'm going to get in the numerator, and then I'm going to factorize it with the midterm breaking method in order to get the possible factors for further simplification. Okay, that's how the 5k is here. Now the quadratic equation is quite clear to us, and let us now factorize this quadratic equation. Okay, in order to get the two factors so that I could cancel one of them in order to get the desired form, this. Okay, so you see what you do, you just multiply the constant term with the coefficient of the highest power variable over here, so it gives you 4. So once when you just find out all the possible factors of your 4, they are this. Okay, and this pair on addition giving you the coefficient of the midterm. Okay, so let us put down over here. So one k is going to be written with this number and another k is going to be written with this number. Okay, so it looks like this. Alright, now you can see that in the first two terms you're having 2k common, and in these two terms you're having nothing common. It means you're having 1 as a common number outside. So let us factorize this thing. So you see in these two terms 2k is common, so let us write 2k is common, and inside the term I'm having just k plus 2 common left. Then I'm going to write this sign as it is, and in these two terms nothing is common. It means 1 is over here, though we do not write this one, but just for understanding I'm writing for you people. That's it. So now you just write the factors. common factor is written just once. It's written just once. And another factor is going to be written by combining these remnants. Okay, so this is it, upon 2 times 2k plus 3. Okay, so this 2k plus 1 and this 2k plus 1 got cancelled, and what is left now are these two factors in the numerator and this in the denominator. Okay, that's it. So you see, this form is right equal what we obtain in the rough work over here. Okay, so it is exactly the same. So it means my P of n is true for n equals to for all n for all n equals to k plus 1 if it is true for n equals to k. Okay, so what statement do I have to write here? Let me write first. So as the principle of mathematical induction has satisfied, and it is now proven that this series on summation give you an answer which is right exactly equal to this general form. Okay, so thus P of n is true for your n equals to k plus 1. So according to the principle of your mathematical induction, the given P of n, which is actually this is true for all n belonging to your natural number. If it is true for your 2, then it is true for your 2 plus 1, that is 3. And if it is true for your 3, then it is true for your 3 plus 1, 4, and so on. It carries all infinite natural numbers. So that's how we just perform the principle of mathematical induction, and I hope that this video will help you in getting the concept and in applying this entire methodology of mathematical induction on typical series given to you in the questions and in your exams. It would help you. So if you find this video helpful, then I appreciate if you please subscribe my video and just hit on the like and share it with your buddies. Okay, so long then, and inshallah I'll see you in the future with some more helpful videos.